Okay, so welcome to the second part of the week 3 lecture, and we're going to continue with our contents, and we're going to cover the geometric dimensioning and the tolerancing. So we start with the topic, and we're going to talk about the definition of that. So in general, a language for communicating the engineering design specification is going to be the geometric dimensioning and the tolerancing. This includes the symbols, the definitions, and the mathematical formula and the application rules. The convey of both the nominal dimensions, like the basic sizes, and the tolerances for the parts. The geometric dimensioning and the tolerancing is not a creative design tool, and it cannot communicate a design intent for info about the part's intended functions. For example, we have this bracket, all the dimension has been shown, so we can simply express the same dimension as a new geometrical design. So now we can see that we have a cross section to tell us what the internal details of the section AA, which can be cut in the half, and also we can put some dimensions about the diameters and their tolerances, for example, and the angles and their the distance between both. So you can see that here say that 5x 72 degree, that's mean we're going to have 5 holes, and difference between them is going to be 72 degree. The whole of the cylindrical part here, for the external one, is going to be the 6 inches plus minus 0.02, and the inner one here is going to be the 4.5 plus minus 0.015. So that's how to do the dimensioning from a simple shape to a more detailed one. The geometric dimensioning and the tolerancing in general are going to use a set of samples for the example tolerance, and what will be the characteristics and the symbols for the process. So for example, from, we can use the straightest line. For the flatness is going to be the parallelogram. Circles, we're going to have the circle. For the cylindricality, we're going to use a circle with two tangential lines. For the profile, we're going to have the profile of the line to be just an arc. The profile of the surface is going to be half circle. The orientation, we can have the angularity, we're going to have the angle sign, and the perpendicularity, we can have the two perpendicular lines, and parallelism, two parallel lines. For the locations, we can have the position of the symmetry, which is going to be a circle with a cross in the middle, and the concentricity is going to be two circles inside each other. For the run out, we can have a circle run out, which is going to be just an arrow, and the total run out is going to be two parallel arrows connected at the base. If I would like to have the features for the control frame, I can have the square, which is going to have the geometric characteristics, which can be, as we mentioned once again, the concentricity, or I can have the circle with the cross in the middle. I can put the phi, which means is diameter, and the tolerance of that diameter, and the C is going to be the datum center. Again, I can use that as following. It's going to be the circularity, going to have the tolerance of 0.01, and the diameter is going to have the tolerance of 0.025. The standard symbols, all the standard symbols according to Australian standard of 1100 are listed in this slide, in these tables. So these are the general dimensioning symbols that we already covered them earlier. These are going to be the surface texture samples, like the basic surface texture sample. The machining surface is going to be mandatory. For example, I'm going to have the triangle to be closed at the bottom. If I'm going to put a circle on the top, it's going to remove all the material from the surface, not going to be permitted. The tolerance specification symbols are given here. This is the feature identification. That's for the datum features identifier and the dimension datum. The datum target, and we continue with that all the way down. So it's going to be no time actually to read them all. Now, some of the definition of the shape we have. Now, the same section that we talked about, the cross section of that, you can see that here we're going to have the feature which has the cylindrical tolerances zones, whose size is going to be phi of 0.03 and the maximum material conditions and its positions to a datum datum A primary and the datum B secondary. And we have maximum material conditions. For that surface here is we're going to go to the datum A within the cylindrical tolerances of 0.01. At maximum material condition, the datum feature is going to be B, and we continue reading that. So I don't want to read that. I would like you to just compare between the definitions we have here and the symbols that we have been used. So once again, this is phi of 7, and we're going to go to this symbol here, that's centric, and we're going to have the tolerances to be mentioned, and we have the A and the B, which came from the previous table. So some definition for the size we have is, for example, we're going to have some cross-sectioning, and this is going to tell, for example, that this cross-section is going to be for the key seed that use number 7 woodroof key for cutter. So it's going to even tell me what the type of the cutter I can use by explaining with the arrow. Here we're going to have the 1.5 by 45, and this will be the cut we are going to have here for the edges. We don't have actually any, that is chamfer, but we don't have any types of the rounded edges. So we can see that actually we put all the dimensions here. Most of them are going to have the maximum and minimum value, and this we can find the tolerances accordingly. And it's defined the keyways with all the dimensions that the cross-section AA was going to be shown at that point. So some of the dimensioning we again have, some of the symbols are going to be placed in front of the dimensions. For example, the phi is going to be dimension that refers to the diameter of the circle, so it should be phi followed by a number. The R, which dimension refers to the radius of the part of the circle. Once again, we're going to have the R, then followed by the number. Dimensioning all the functional features like the avoid all the confusion and use most of the descriptive views. So the placement of dimensions should be unobstructed as much as possible. So that will be too much obstructed between the lines, as you can see here. We should avoid that. We are going to have the lines that not intersecting, so or minimum intersecting like here. We should do that, and here we should do that. But this will be multiple squares are going to be generated. We need to avoid having such situation. So that's something we need to actually be aware at, because this may confuse the reader about where the lines are starting and ending. Well, by the way, if you had to, then you can keep it. So some of the dimensions should be all unidirectional or all aligned to the features. So for example, once again, here we have the dimension to be unidirectional coordinate standard. So you can see that we have the 2 and 1. Here we have the 2 and 1 with the horizontal line. For the aligned or the standard one, we should actually always have the number to be parallel to the lines of the dimensions. Dimensions should also be placed outside of the part where possible. So you always try to never do that, never put them inside the part, because this will give the idea of, okay, now the part is empty from inside. So we're always going to take them out, and this will be the correct way. Avoid the over dimensioning. So here we don't have to actually tell what the distance from this point to that point and distance from this one to that one, and then the total distance. So if I get to remove the C, this should be okay, because this will be a direct dimensioning. And if I get to make it that way, it's going to be indirect dimensioning. So distance from that point to this point can be found by subtracting the A from the B. So the sketches on the SolidWorks must be fully defined, not over-defined or not under-defined. Some of the international tolerance grades, or the IT, It's going to be reading like that. So we're going to have 50H8. That means the 50 is going to be the basic size of the hole. The H8 is the tolerance grade, H capital 8. So the H means the fundamental deviation we're going to have, and the 8 is the IT, or the international grade, tolerance grade. If you remember that, right? These are the grade we're talking about. We say that the 1 to 8 is going to be for measuring tools. From the 4 to the 11 is going to be for the fits. From 8 or 7, usually from 8 to 15 is going to be for the material, and from the 12 up to 16 is going to be for the large manufacturing tolerances. So now that's for the hole, that's for the shaft. So for the shaft, once again, we're going to have the basic size, and we're going to be told about the fundamental deviations, which is going to be the small f, and the international tolerance grade value, which is 7. So from here, I can know what the tolerance grade, and then I can put the plus minus, or only the plus, or only the minus. If I get to have the fit between shaft and the hole, then I'm going to write it down as 50. That's the basic size for the shaft and the hole. But for the hole, we're going to have the HA types, and for the shaft, we're going to have tolerance to be the F7. So there are sets of tolerances that varies according to the basic size and provide a uniform level of the accuracy within the grade. The tolerance symbols are used to specify the tolerance and fits for the mating parts. For the hole basis system, the 50 will indicate the diameter in millimeters. The fundamental deviation for the hole is indicated by the capital letter H, and for the shaft is indicated by the lowercase letter f. The numbers following the letters indicated in this IT grade, note that the symbols for the hole and the shaft are separated by slash. The tolerance symbols for the 50 mm diameter hole may be given in several acceptable forms. The values in the parentheses for the reference only and may be omitted. So once again, these are some of the examples. That's for the hole. We have the 550H9. That's the preferred one. Well, we're going to say that, let's put this here. And for the shaft is going to be 550D9 small. So that's what we can read from the table. So if I'm going to go for the free running fit hole basis, I can write it down once again that the phi is 50H9, and that means that the tolerance is going to be 50.062 maximum diameter and 50.000 the minimum diameters. Or we can say that the tolerance is going to be plus 0.062 and minus 0. The same thing for the hole. You can see that the diameter is always going to be less than the 50, and thus both are going to be negative tolerances. And the main reason for that is that we need to have a free running fit. And once again, we can write it as the maximum and the minimum diameter for the shaft and the hole. So the next video is going to be about the fit, where we're going to cover the tolerances, allowance, and the clearance, and geometric dimensioning and tolerancing, and the clearance fit, the interface fit, and the transition fit. And also we're going to cover the part of the dimensioning and the tolerancing in the SolidWorks that we're going to apply during the lab session for this week. Okay, so thank you very much, and we're going to waiting for your question during the lecture time.